Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Sharon Goldberg here visiting us from Boston University. She was a postdoc at MSR New England and has been very involved with various research efforts at Microsoft Research, and so we're very pleased to have her visiting, talking to us about finding incentives to secure internet routing.
Okay, hi. Thank you so much for having me and giving me this venue to speak. So what I want to talk about is a problem that we've been working on for about 2 years. We've been trying, well, for 3 or 4 years, but this particular problem is we're trying to understand why the secure routing protocols, which from a cryptographic perspective and a security perspective are pretty trivial, the protocols themselves, why is it so hard to actually get them used in the internet? So what we're trying to understand is the incentives for really deploying these secure routing protocols that will prevent a lot of attacks. Why is it so hard to do this, and what ways we might use to encourage people to actually deploy them? So this is 2 different papers, actually 3 different papers I'm going to talk about. Joint work with Philippa Gill, who's a student at Toronto, Pete Humman, who was a student at Princeton when I worked with him, Zhenming Liu, who's a student at Harvard, Jennifer Exford, who's my advisor, and Michael Shapira, who's been my collaborator for the past 4 years. He's going to be at the Hebrew University very soon. Okay, so what I want to talk about today is start off by showing some of the attacks that we worry about in interdomain routing. So in particular, we're going to be focusing on the security of the global internet routing system and attacks on it, and some of the security protocols that have been proposed to defend against these attacks. And if you look at the security protocols, you're not too excited about how novel they are. That shouldn't surprise you. They're very simple. The real focus of the talk is trying to understand how do we actually get networks to deploy these secure routing protocols. And to this end, I have 2 different approaches that we've been working at for the past 2 years. One of which is because it somehow improves their security. So ISPs or networks have an incentive to deploy secure routing because it makes their networks more secure. Right? That seems logical, right? But that may be a little bit of a hard sell to networks. So one of the other approaches that we propose is not because they care about security, but because it's somehow going to impact how much money they make. Okay, so they're going to somehow lose money from their customers unless they become secure. And we're going to do a study of seeing how this actually, the dynamics of how this all happens. So before I start talking about economics, let's focus on the actual problem. So the setting that we consider is the global internet routing system. So you can think of a graph where each node is a network. So for example, level 3 is an ISP. This is an organization that provides backbone service across the world. This is China Telecom. You can see it's a residential provider in China. This is Verizon Wireless, and this is another network owned by Verizon Wireless. So you can see that each one of our nodes is a giant network. Inside the node, there's hundreds of routers. But we're not going to worry about that. We're just going to worry about the view of these networks talking to each other, and that's the system we're going to analyze. So what this system does is it sets up paths from ASs, so we call these ASs autonomous systems, these nodes, to destination addresses. So you can think of this is an IP address that all these guys want to reach. And when you think of IP addresses, we sometimes think of IP addresses being mobile. Okay, don't think about them this way. IP addresses are allocated to these particular networks. So this IP address belongs to this network 22394. Okay, that's the number of the network. And this is the IP address block that belongs to this network. Okay, so what's happening here is this is the routing protocol message, and the routing protocol message is saying, if you want to reach this IP address block, then route to 22394. Okay, yep. Okay, so /24 means that the first 24 bits specify the block of addresses, and the last remaining 24 minus 32 bits is sort of all the different addresses that are subparts of this. So we call it a prefix, right? So this is a contiguous group of IP addresses with the first 24 bits being this. Okay, so you can have different groups. You can have /24, /22 is a bigger group of IP addresses, /8 is a bigger group of IP addresses. Okay, so this block belongs to this network. And so this is how the routing protocol goes. And let's assume that this network routes this way, its traffic, when it to reach this IP prefix. And then when the next network wants to announce how to reach the prefix, it does what's called a path vector protocol. So this protocol is BGP, a path vector protocol. What it's doing is it says the path to reach this prefix is Verizon Wireless and then this network. Okay, so everyone, when they announce their path, they just put their name in the path, right? So the next guy is just going to say the path to reach this prefix is level 3 Verizon 22394. Okay, that's what the protocol does. It puts down paths. Each node in the path puts down its name, and it says this is the destination we're trying to reach, this block of addresses that belongs to this guy. Okay, and that's the system we're going to focus on securing. Okay, so just to say a little bit before I get into the attacks, the reason that this is interesting is each one of these networks is a separate business, right? They're not under a single jurisdiction. They're owned by different companies. So for example, Microsoft is an example of one of these networks. And when we want to actually go and upgrade the routing protocol, we have to find some way of making all these different networks that are controlled by different entities actually agree on doing an upgrade. And that's not easy to do, because it's not like, Windows wants to do an update, Windows does the update. It doesn't have to tell anyone else because it's just Windows, right? In this system, we have multiple companies that have to cooperate with each other if we want them to actually change what they're doing. Okay?
And the topology of the network is basically like a set of trees, and the next level is
it's not exactly a set of trees. You can think of the topology of the network in the following way. So think of the core of the network, what we call the tier ones. There's a very small number of them, like you can think about 15-ish networks that are all sort of connected to each other. And then from there you have these trees, but they're not really trees. Like they're sort of, a node here might be in multiple trees. So it doesn't really look like a tree. It's sort of, there's sort of these offshoots, like two-level offshoots from them, but one node may be connected to this tree and this tree too, something like this. So we'll talk more about the actual structure of the network later on in the talk. Okay, so let me show you an attack. So who heard about what happened with China Telecom in April 2010? This was in the New York Times. Okay, so let me show you what happened. So what happened was there was a router here, and and by the way, this is from data that we actually looked at. So there was a router here at China Telecom that claimed to own a set of IP prefixes. So actually, this was the address that's really owned by this guy, right? This address really lives here, but this China Telecom router was lying and saying that it owned this address. Okay, and it wasn't just this set of addresses; it was 50,000 different addresses. Okay, and so this is obviously a lie because the address belonged in this example to 22394. Okay, so what happens? So let's look at ISP1. So this is an actual ISP that I've anonymized. What does ISP1 get? So it sees two announcements. It doesn't know where the prefix really belongs. So it sees a long one, 3 hops, and a short one, 1 hop. Okay? So it has some process of deciding what path it's going to choose, and it turns out that in this case, this path was shorter, and so it routes this way. Okay? So really what happened was the traffic from this ISP1, which was a large ISP, actually went to the wrong place. It didn't go here, it went over there. Okay, so that was the attack. Even more interestingly, there was some interception going on. So what happened was there was some honest router here. Well, anyway, a router that wasn't misconfigured that knew how to reach the actual destination. So it routed that way, right, through level 3. That's how you really go. And then the cool thing was the traffic went internally through the China Telecom network, went out the other side, and went to its destination. So what ended up happening is we call this a traffic interception attack because the traffic was traveling through this network and went to the destination. Nobody saw any disruption in service for these set of prefixes, except that they were sort of controlled by this network for a little while. So this is the kind of stuff we worry about in this space.
So what is the problem? It's just ISP1, it took 5 hops instead of 3 hops?
Yeah, and it was potentially going through a network that it didn't know it was going through. Like it didn't want the traffic for this destination to go through that network. Right, so the idea, yeah, so when you look at this as a cryptographer, you say, okay, well, this should just be, if it's sensitive data, it should be encrypted, it should be authenticated, it should never be going through the China Telecom network, and that's what we'd like, right? But that's not actually what happens with all of the traffic that's going through these networks. So
essentially, if I want to send a packet, I have a way to say, please don't route it to some. I never saw that BGP does something like that.
I mean,
like this ISP1.
Yeah.
So there is a way. I saw that BGP is a particular product. You don't care where it goes to as long as just takes the shortest path or something.
Well, okay. So what's wrong with this case is that technically what's happening here is that this ISP1 is thinking that this prefix belongs to China Telecom, but it really doesn't. It belongs to this one. So this is sort of an incorrect piece of information. The correct piece of information that should have been here was 22394 and then the prefix, right? So we look at this as an attack because the decision from this ISP was that this is the way the traffic should go. So, I mean, one way to look at all of this stuff, and we have argued this, in fact, I've even argued this a couple of years ago, was that, don't assume BGP sends your traffic anywhere that you think it's going, and just encrypt and authenticate all your traffic, okay? But in reality, people don't encrypt and authenticate all their traffic, and so this is why we worry about this kind of attack. So this is false routing information propagating. Yeah.
Yeah. If you encrypt and authenticate everything, this is still a denial of service.
It could be a denial of service, yeah. So
denial of service, right?
Yeah. So you have denial of service.
No crypto can.
So availability attacks are a big problem. Yeah.
Did they put their name in the list so you knew what to do?
No. No, so what this guy saw was a short announcement through China Telecom, but the real path was ISP1, China Telecom, level 3, Verizon Wireless, blah. But what ISP1 saw was this. Okay?
No, but did you say that as it goes through, it appends the name of the path?
Oh, okay, so let's distinguish between the routing announcements and the traffic flow. Okay, so what you're seeing here is just routing announcements. It's saying, if you send traffic to me, this is how it's going to go. Okay, the traffic itself, as it goes through, it doesn't get written. No writing is, the packets are not written with the path they traverse. They just go there. Okay? Does that make sense? That's a really important point. These are just routing announcements. So think of them like one announcement every 5 seconds as opposed to packets every 2 nanoseconds. Packets every 2 nanoseconds don't get written with their path. That's too expensive.
Okay. So how much announcement is made like from each node? You don't obviously announce all the paths from you to everywhere else. How much do you announce?
You do, actually. You do announce all the paths that you're willing to carry for everyone. So basically there's 300,000 prefixes in the internet, and you would make announcements for all 300,000 of them to your neighbors for which you're willing to carry traffic for those prefixes. Yes. That's how much traffic you have. Okay, so slide number 1. So let's go to slide number 2. So this is bad. Okay, so now what's actually nice is that we've been working on this problem for 20 years. And after 20 years, I should impress upon you the excitement that they're actually deploying a PKI for this system. Okay, and this took 20 years. So this is actually happening. Like if you go to network operator conferences, which I went to last week, half the talks are on this, how you should get this into your network. Okay, so this is very exciting. And what they have here is this public key infrastructure that's a PKI, which assigns basically public keys to these networks. And in addition to the public keys, it also assigns a mapping from IP prefixes. So it'll have an entry that says, this prefix belongs to 22394. Okay, and that'll be included in the database as well. So there's an allocation of addresses to ASs as well as public keys. So of course that the attack we saw before, to all of the crypto people in the room, this is not going to succeed, right? Because we can check the RPKI, see that China Telecom doesn't own that prefix, and this announcement should get dropped. Okay, so the thing that we tell operators is that this would stop most of the attacks we've seen to date, because most of the attacks we've seen just look like this. It's a false announcement of a prefix you don't own. Okay, now, okay, but of course, you know, if we have really malicious attackers, so here's a hypothetical situation, the malicious attacker can still fool the RPKI if it wants to do the attack we saw before. All it has to do is announce itself, right, attached to the actual destination that owns the IP address, and then the attack will still succeed because this path is shorter and he wins. Okay, so obviously RPKI on its own, just having a mapping from prefixes to the owners is not going to stop all possible attacks. So, you know, I think in 5 seconds, every single person in this room can come up with a solution to now that we have a public key infrastructure, how do we prevent this kind of attack? So we'll use digital signatures, right? So basically, we have this protocol called BGP-SEC or Secure BGP. You may have heard of it. All it is the standard thing that we would expect with digital signatures. Now, instead of announcing the prefix in the clear, you're going to sign it. So what this says is, I'm 22394. Here's the prefix you want. And Verizon, I authorize you to use this announcement. Okay? And then that whole business gets signed by the key of this guy. Okay? So now we can see we can start building up chains of signatures where because you've signed the forward hop saying Verizon's authorized to use this, you can start chaining this together and see that when you get an announcement, everyone on the path has actually made the announcement. Okay? So what are some of the, so that's the solution to these types of attacks. Now, is any questions on that before I go on? Okay. So what are the challenges in deploying this protocol? Well, first of all, it's an online protocol. Right? So whenever you have an announcement, you have to sign it. That means you have to pull out your public key and do the signature. Right? There's also a need for keeping a cache with lots of public keys so you can do the verifies because you're getting announcements from all over the internet, right? Because you need to know how to reach every destination in the internet, which means you'll eventually get a signature from someone really far away. You're going to have to verify. So there's a lot of overhead involved in deploying this, and it's very expensive. So that's really the reason that, that people sort of have argued against using this. Another interesting thing, okay, so obviously this doesn't work, okay. So the attack fails, right? Because the attack before, he couldn't announce this path because he doesn't have a signature saying that he's authorized to announce a path to that prefix through him. Okay, so, so another interesting thing, about this setting is that we have to consider partial deployment scenarios. So like I said, each one of these networks is owned by a different company. So we're never going to be living in a world in which one day everybody wakes up, turns on their router that's equipped with the latest crypto accelerator that can do lots of signatures really fast, and boom, the whole internet is secure, right? That's not going to happen. We're going to have multiple islands of secure networks. Some people are going to be on, some people are going to be off. And so one thing that scares network operators is the following. Let me first show you, let's consider the following scenario. Let's imagine our China Telecom router is doing the same attack as before, right? This network is going to be insecure. Let's assume he hasn't deployed secure routing. All of these guys have deployed secure routing, right? So if this network here gets these two announcements, right? If it just says, okay, the path is shorter, then the attack will still go through. Right? I'm saying something very obvious here. But what the point is that if this network, the one that's secure, doesn't use security in its decision process, it doesn't change its routing based on security properties, then the attacks will still go through. Okay? So something that scares network operators, in addition to upgrading their routers and having all this expensive hardware in their routers, is that it'll change their traffic engineering. And if you think of what these blobs are, these are hundreds or thousands of routers that are engineered to have particularly, certain capacity links between them, and everything's designed right within an inch of its life. And if all of the traffic in the world just shifts in one direction because of security or not, then you can have big issues, right? So even convincing the operators to turn this on and use this in their decision process is a big deal. Okay? Yeah.
Is it true that in your threat model you preclude any possibility of collisions?
I haven't even given a threat model, and I'm not really going to in this talk. There are works that look at threat models. I'm not going to even talk about security in this talk at all. I just wanted to motivate why the protocol is needed. But
it seems like even when deploy this kind of public key system,
yeah.
if China Telecom and Verizon collude, they can still announce as a legitimate owner that IP address.
Yeah, exactly. So it's very vulnerable to those types of collusions. People don't really worry about them as much. Just because I don't see a good way to prevent those kind of collisions.
Yeah, I'm just wondering how that impact on the incentive that you just bring up about the deployment of this kind of.
Yeah, so one thing is when I'm going to talk about incentives for deployment, I'm going to sort of divorce the security considerations from the incentives in some sense. So we want to eventually get to a world where everyone's secure. So I'm sort of going to think about how do we get there and not exactly what happens along the way. That's sort of what we're working on now. But in terms of collusion, I haven't seen anything that's really satisfactory. And in some sense, I don't know how to do anything, because if these guys are in collusion, then they can share secret keys and start doing all kinds of stuff, right? So yeah, it's not really something people worry about too much. Okay. So the point is, routing policies have to be impacted by security as well. Okay, so just to recap, why is it taking so long to deploy this stuff? And when I say so long, Mariana's advisor has been working on this for 20 years. That's what he told me when I talked to him. He's one of the people that I work with on this stuff. So for many years, they said that we'd never have a public key infrastructure. If you think about it, there's a lot of politics involved, right? You have to get Russia and China and the US to agree on a single root of trust. That may not be so easy, right? But now it's actually happening, believe it or not, and these political issues are somehow actually being sorted out. It's kind of amazing. So you actually have the Asia routing organization and the US and the European routing organization sort of all advocating for the same RPKI. So it's pretty exciting. So now that this is happening, this problem becomes more realistic. It's more realistic to start thinking about actual secure routing deployments. But now we sort of have to think about what's going to drive these ASs to do the deployment locally. So first problem is they're economically motivated. They're not just going to turn it on when we say turn it on, right? It costs them money. And the second thing is that if you think about how these systems look, imagine you're the first one to become secure. Nobody else in the world is secure except for you, right? What have you gained, right? You've gained nothing, because you can't sign anything from anyone. You can't send anyone signatures because no one can read them, right? You can't read anything else because nobody else has keys. So sort of the initial adoption, initial benefits of adopting this thing are very low. Okay, so we need some way of sort of creating a large number of people that are secure so that they can start signing things for each other before the protocol will even do anything at all.
So Sharon,
yeah.
Maybe I'm missing. So
yeah.
It's just. So it seems like you're saying that this thing is going to be deployed, so presumably somebody is pushing for it. So imagine somebody is like those 15 top-level guys. So the way it usually works, they will just agree on a date like August 1st, 2011. and we have some internal testing, and on August 1st, 2011, there will be 15 public keys. So what's wrong with that? Sorry, I'm just...
What's wrong with that?
Sure
Okay, so
yeah.
so that is actually the scenario we consider. There are some issues, so what's wrong with that? Can I answer that question later? I mean, it's just like what Yevgeny's saying is like we have, so there's 36,000, let me put some numbers. So there's 36,000 networks in the world, okay? And there's 15 top-level guys, right? And this is very nice for us, actually, because if you want to look at the degree distribution of this graph, it's like 1, this is 30%, 2 is 30%, 3 is like 15%, okay? And then it's like up to 1,000. Okay, so it's a really, 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 really skewed degree distribution. Okay, it's extremely skewed. So yeah, like what Yevgeny's saying is that the top-level ASs should deploy, that should be enough, right? So that's actually what we simulated, and we showed that that does actually work under some set of conditions. It doesn't always work. You need to create the right set of conditions, and that's what this work is about. How do we create the right set of conditions for that? Okay, so that's, yeah.
Are the people who are pushing this technology different from those 15 guys? So it's the same? You're saying it's finally happening, so somebody is making it happen. I'm trying to see if it's the same.
So this
15 guys,
is not finally happening. Only the PKI is happening. This is happening. PKI is happening. It's a combination of governments, the top guys, Cisco. There's these things called routing information registries, which is where you have to register your IP addresses. They're pushing for it. You go to the network operator conferences. There's a very strong social network. It's sort of a lot of peer pressure. So it's not exactly like the top 15 guys. There's all these organizations that are in play here. This thing is not happening. This thing is only being standardized right now. And so if you're working on aggregate signatures, for example, this is your application, right? So there's actually a new standard that has many different requirements that are interesting for aggregate signatures. We actually have a paper on that right now. But this is not happening yet. This is like 10 years out or 5 years out. So this is our setting. And now what we want to understand is how can we create local incentives for adoption that will drive global deployment. Okay, so this is a very common problem in the mechanism design social networks literature. So this is a very beautiful paper for computer scientists to read. So I really recommend reading it if you're even remotely interested in what I'm talking about today. So there's a paper called Technology Adoption in Social Networks. So what's the idea? So basically you have this game, and it's a graph, and nodes are going to deploy the new technology, so in our case it would be secure routing, when their utility, for some measure of utility, exceeds some threshold, right? So if I get some utility from the protocol, I'll become secure. And all of these models basically look at the following thing. For example, am I going to go see a movie? Well, I'll go see a movie if enough of my friends tell me the movie was good and I should go see it, right? So all of these utility models are a function of your immediate neighbors, okay? Our setting, that doesn't work, right? Because in our setting, what we want is paths to destinations. So I want to reach IP addresses that are far away on the other side of the world. So my utility won't only derive from what my neighbors are doing, it's going to derive from how many paths I can see. So fundamentally, our problem is different from all of the problems that have been considered that base themselves on neighbors. Okay, so technically it's a different problem. There's also been like sort of folkloric and all kinds of discussions about how we can do protocol adoption, like new protocols like IP version 6. So if anyone's interested, there's currently IP version 4. We ran out of addresses. There's IP version 6, which gives us more addresses, right? So people have been talking about how do we get to IP version 6. So one thing people say is if you're not up to the latest standard of whatever protocol you're supposed to be using, you're going to lose customers. Okay? So people have talked about this idea. Nobody's actually shown that it'll happen, and that's what we're going to do. Okay? So we actually run simulations and show that this is exactly what happens. Okay, so that idea was out there in the literature. And then there were some works that talk about how if you have a large enough group of people deploying, then the security incentives increase, and so you're going to deploy because you want the security properties. Okay, so there's sort of two approaches. One of them is you want money, customers. You don't want to lose your customers. The other one is you want security. Okay. So what we do in this work, these set of works, is that we're trying to develop guidelines for how you should deploy these protocols. So who should the early adopters be, like what Yevgeny suggested? How does it interact with routing decisions, right? How does it impact routing decisions? And the approach we're going to use is going to be to leverage the properties of the internet graph. So I'll tell you a bit later about what the internet graph looks like and what properties we can use. But our approaches are really strongly tailored to the specific structure of the internet graph, which is very interesting, like in particular with this kind of degree distribution and other things that I'll show you. Okay, so now that we develop our guidelines, how can we evaluate them? And that's where we need modeling. Okay, so I don't look at these works as just modeling. the models exist to evaluate the guidelines. So the model involves how do we model ISP utility, how does routing happen. We use the same sort of framework as Morris and Kempe-Kleinberg-Tardosh, which is that ISPs are myopic and they're going to upgrade if their utility gets high enough. Okay, so we of course need to figure out what utility means for our context, but we use the same sort of idea. We analyze the model for tractability and convergence, which is the basic step, but the really interesting step is running simulations. What we do is we take maps of the internet, or our best guess of what the internet looks like, and simulate these deployment processes to see if they work. Okay, and these simulations are quite large scale. Okay, questions before I go on? Okay, so now I'll show you some results. I want to show you two different works that we're doing. The first one is a more stylized, more theoretical. It's a very pretty theoretical model. And in this model, we're sort of assuming that ISP's utility depends on how much security they get from the protocol. And then I'll show you a more realistic kind of work, much more simulation-based, where ISPs are going to upgrade because they care about revenue. Okay, so let me start with the first one. So here's the problem that we define. We have an input, which is a graph, and each node is given a threshold. So this is node 7, and it has threshold 4. Okay, so this is the input to our problem, nodes, a graph and a threshold. Initially, everyone is insecure except for the early adopters. So let's assume that, these guys are the early adopters. And now each node is going to become secure if his utility exceeds his threshold. Right? So at the end of the game, we want everyone to be secure, but we want to find the smallest set of early adopters that will cause this to happen. Okay, so if you've read Kempe-Kleinberg-Tardosh, this is very similar, except that our utility function is given by the size of the secure connected component adjacent to a node. Okay, so let's look at what that means. So if we look at the utility of this guy, his utility is going to be 2 because he can reach 2 nodes that are secure from his network. Okay, and if we look at this, so he'll turn on because his threshold is 2, he's got 2 nodes he can reach, and that's enough for him. If we look at this guy's utility, his utility is 3 because he can reach these 3 nodes, and so his threshold is 2, and so he's going to become secure. Okay, and that's how the game goes. And what we want to do is find the smallest set of early adopters that we can.
So this is an iterative game, right? So
yeah,
that is 3 because only after the 4th guy turned on. So it's
yeah, so there's sort of rounds, and it's sort of a cascade. So you want to figure out who should be the first set of nodes that you turn on, so this thing cascades and the whole network turns on. Okay, and
what's the motivation for the differing thresholds? I mean, like just their cost to upgrade?
Yeah, so the threshold will represent a cost to upgrade. So this is really a very general formulation of the problem.
Bigger, like what accounts for that?
Actually,
like
at this point,
at
this point, I don't have a good argument for what threshold should be assigned for what person. At this point, this is really like much more theoretical, and the next set of works I'll show you is much more grounded. But this one is more about like, is there a way to actually figure out who these early adopters should be if you had the graph and if you knew the thresholds, right? And there's actually a huge amount of work on this in the like mechanism design EC type of people. It's Sigmod, KDD, those people. They've done a lot of work on understanding like what the threshold should look like. Like if the thresholds are random, can you get better algorithms? If the thresholds are not random, it becomes much harder. We haven't been able to do anything with, giving models to the thresholds very much with this particular problem. Yep.
Could you explain from an ISP's perspective, what does it mean when the utility exceeds the threshold?
Yeah. Okay. That's what I wanted to talk about. So why did I choose this utility function? We chose this utility function for the following reason. What this looks like to him is, if he's sitting here and he's saying, if I became secure, how many places in the internet could I reach along paths that are secure? So what this is saying is if I can reach a destination here and I can reach a destination here. So that's sort of 2 destinations that I can get to that are secure. Right? If I continue, for example, what this guy is getting is if he becomes secure, he can now walk to 1, 2, 3, 4 places along secure paths.
Unless it can become secure.
Yeah, so basically you can't, so the way the BGP protocol, the way the signature protocol works, you only have guarantees that everyone announced the path if everyone on the path was already secure. So a path is only secure if everyone on that path is secure. Does that make sense? So you're sort of only looking at the secure connected component because, for example, if this guy was secure here, it's not going to contribute, well, I need another node, but if there was some other node here that was secure, it wouldn't contribute to the utility of this guy because he can't reach it along secure paths. So he's only looking at the nodes that he can reach because those are the only ones he can get secure routing announcements from. Does that make sense? So this is a really, really stylized, simplified model of this problem. Okay. Okay, so we came up with this problem in 2009, okay, and I couldn't solve it for a really long time. And then Zhenming came along. Okay, we knew it was hard. So it's NP hard. Guess why? Because of set cover. Okay, so I think most people here can probably come up with that. Okay, but after 2.5 years of not having any results on this, Zhenming has figured out how to do this. So here's the result that we have with Zhenming. So suppose the graph has a small diameter. So what does diameter mean? The distance between any pair of nodes. Okay, so actually the internet graph has an extremely small diameter. On average, it's 4. In the worst case, it's like 11. Okay, so it's extremely small diameter. So suppose you have a graph of small diameter and you have a small number of thresholds. Then we actually have an approximation algorithm to choose the optimal early adopters. So our set is going to be too big. We're going to be off by this much. So radius squared times the number of thresholds times log squared the number of vertices. I think the squared is gone now, actually. But yeah, the squared is gone. Okay, so what does this mean? So suppose that we only have, so suppose the set of thresholds that nodes can have, suppose there can be only 2, 4, and 7. Right, that means I have a total of 3 thresholds. Okay, so that's the parameter here, t, how many thresholds I have. Okay, so why does this work? So if we think about this problem, think about a graph where there's a blob of secure guys here and a blob of secure guys there, and they're not connected. Okay, imagine someone in the middle turns on, and these 2 blobs now all of a sudden are connected. That means that the utility of everyone surrounding these 2 blobs has just shot up by a lot, right? The idea is that if this is secure, and this is secure, and all of a sudden this guy turns on and bridges them, then the utility of everyone here is just changed dramatically, right, the moment that this guy turns on. What Zhenming observed was that if you assume that the set of people that are turning on are always connected, so if there's only one secure connected blob, someone new turns on, the blob grows by 1. Right? Another new person turns on, the blob goes by another 1. So it's very easy to keep track of the changes in the utility of each of the nodes. So what he observed was that if we can make sure that the early adopters are connected, then this blob grows in a very controlled way, and we can actually build this into an LP and solve it with an LP. Okay? When we have this kind of complicated jumps in growth, when these different blobs get connected, then we didn't know how to deal with the problem. And so to me, that was the big insight in this problem. Okay, so we haven't actually run any simulations and seen how it works yet, but this is the approximation. Yeah.
So why is it the case that these blobs only grow by a little bit? That's the way the algorithm works.
Yeah, the algorithm is designed so that if the early adopters are connected, then the blob is always going to be connected, because anyone who turns on has to be, the only part that's on is going to be one component, and anyone who turns on has to be connected to that component, otherwise it has utility 0. So the blob always grows by 1 at each time. That's why
it becomes worse with the diameter.
Yeah, you have to make sure that everyone's connected. So if the optimal guys that you should turn on are these 3 guys, but they're not connected, you just connect them all, and then you lose a factor of r. Yeah.
So the main difference, if I understand you right, is that now you're saying that I'm going to assume that the early adopters, the people I designed to adopt first, will be connected.
Yes.
And then we look at the algorithm, and this will give some good approximation.
Yeah, exactly. So the LP will solve for it'll search for the optimal solution given that the early adopters are connected. That's what the LP does. And then there's many other things that it does, but basically that's the basic idea. So I can tell you more about this if you're interested. Okay, so that's our theory view, and now we have to be pessimists. Okay, so this was all very nice because what it was assuming that networks, when they see more security, they're happier and they're like, okay, now I'm going to spend a lot of money on my routers, upgrade them all, and become secure. Okay, but the pessimistic view says they're never going to do this. Even if everybody in the world is secure, I don't really care if I'm not secure. It's just too expensive. I don't want to do it. Okay, so what we want to say is that, so the pessimistic view says there's not really any economic incentives to do this. The only gain you're getting from these things is security incentives. And so no one's going to ever do this. Okay, but here's, we challenge this view with this next set of works where we're going to show how this protocol actually has an advantage. Like I showed you earlier, it affects route selection. Right, so if you wanted to have any security impact, it should impact the routes that your network chooses. Right, otherwise it's not doing anything for you. And so because it impacts route selection, it controls traffic flows. And if you think about the way these networks work, they make money by attracting more traffic. They get paid to carry traffic from their customers. That's where their revenue comes from. So the more traffic they carry, the more money they make. So the idea is because route selection is impacting traffic flows, the more secure you are, you're going to draw more traffic into your network, you're going to have more customers, and you're going to make more money. Okay, that's what we're going to use to drive the next model. So that's what this is about. Yeah.
So there is also this question. I don't know if it's addressed by this. That if you're saying that ISP just want to get more traffic to generate more things, they can potentially lie and try to claim that everybody goes through them. So does it address it?
No, it doesn't. It doesn't assume this. So lying is another thing altogether, and we've looked at lying in a separate work. What we're talking about is let's assume that they're not going to lie in this model. Yeah. So how can they? Let's assume the only way they can get traffic. Everyone's going to be honest, but they will get more money if they're getting more customers. So in order to talk about money, I need to tell you a little bit about how money flows in these systems. Okay. So I haven't told you where the money is in the system. So let's start with a very simple model that we use to understand the relationships between these networks. So the first relationships that we have is we have customer-provider. So this is a network that is a customer of this network. Okay, so what's happening here is that this customer is going to pay the provider both to send and to receive traffic. Okay, so you might think of, like let's say Telecom Italia might be a provider to Turkish Telecom. Right, so Turkish Telecom might pay some money to Telecom Italia both to send and receive traffic because Telecom Italia is a much larger network. They have much bigger coverage, and so if you want to reach more distant places, you'd have to pay. Okay, so in this graph, I have two customer-provider relationships. These guys, this is a customer of this one and also of that one. Okay, the other kind of relationships we have is settlement-free peering agreements, a peer-to-peer relationship. So what's happening here is you have two networks, usually networks of the same size. And what they do is they freely exchange traffic because the idea is that the amount of traffic that I'm sending and receiving from this guy is equal to what he's sending and receiving to me. Okay, so AT&T and Verizon have this type of relationship. The other place you see this relationship is, for example, Google has this relationship with almost everyone it talks to because Google wants everyone to get to them as fast as possible so they can see more advertisements, right? So they're not in the business of making money from internet routing. They're in the business of making money from advertisements, so they allow these sort of relationships. Okay, so this is sort of how money flows in this system. And now a little bit more about the structure of the graph. 85% of the nodes in this graph are a special kind of node called a stub. So what a stub is it's a node that only has providers. So this guy is a stub, he has only providers. Okay? So if we think about the stub, do we ever expect to see the stub carrying traffic like this? Right? And the answer is no. Because if it was doing that, it would have to pay this guy to receive the traffic, right? He's paying to receive. And then he's also paying to send over here. Okay, so that doesn't really make sense. So the way to think about this network is it's sort of like 15% of the graph is in the middle like this, and it's actually carrying traffic from one point to another. So this actually happens. This is what we call transit. It goes from A to B to C. Okay, but then there's these 85% of nodes that just basically act like sources and sinks. Okay, and they may have degree 1, they may have degree 2. They're usually low degree nodes that are acting like sources and sinks. So these are sort of customers. These are people who don't make money from internet service. They're just consumers of internet. Okay, so we also have to think about what we're going to do with these guys because these guys are never going to make any money from becoming secure, right? Everything is a cost to them. And so what we're going to have to worry about is how do we find incentives for them also to become secure. Okay, any questions on this? Okay. So here's an example. Suppose everyone's insecure, and let me just show you how routing is going to happen in this example. We have Sprint here, and it's learned 2 paths. Both of them are equal length paths. Okay, so how should it route? It's just going to route this way because there's some tie-breaking algorithm that routes it that way. Okay, I haven't told you what the tie-break is. It was actually a hash function in the simulation we ran here. But anyway, there's some sort of tie-breaking algorithm. Okay, so suppose traffic's flowing this way. Let's look at the incentives now. So this network here has now attracted traffic from Sprint to the customer, and the customer's paying it, right? Which means it's delivering more traffic to this customer, means it's getting more money from this customer, which means it's making more money. Okay, so the idea is because he's serving from Sprint to the customer, his utility has gone up because he gets to charge the customer more. So if these guys all become secure, so I have 3 secure networks here. Sprint learns now 2 announcements. One is secure and one is insecure. Okay, so now let's make this assumption. So this is the first guideline that we're going to make. Assume that secure networks break ties on secure paths. So Sprint learns 2 paths. They're both equally long. He's going to choose the secure one. So he's going to route this way. And now let's look at the utility. This guy's earned the right to deliver a lot of traffic to the stub, but this guy hasn't. So his utility has gone down because he's now serving less traffic to this customer, and he's making less money. Okay, so this is really the premise behind the work, that because the secure routing is going to shift the traffic this way, the utility of this ISP goes up and this ISP goes down, and that's going to create pressure for him to become secure. Does that make sense? Yeah.
Is it common that one customer is served by multiple
yes,
ISP providers?
Absolutely. Yeah. Yeah, very common. So I think it's like definitely more than 3/4, probably more than 3/4, a lot more than 3/4, but I can tell you for sure it's 3/4. Yeah.
Example? I mean, it seems like why would they pay to internet providers? Yeah. I mean.
So usually one is for backup and the other one is for primary. That's one of the examples. So if one of the providers goes down, you want to have another one that you can talk to. Sometimes you do load balancing that way. But yeah, most of them have.
With this 85%, you mean like residential customers?
No. Don't think of them residential customers like you at home. It's not Yevgeny at home. It's Bank of America. It's CIBC. It's Royal Bank. It's like Microsoft is not, because Microsoft is huge and it has all sorts of internet business that it does. But Boston University is a stub. So universities, small businesses, things like that. Does that make sense? So it's not you at home. You at home have only one provider. It's usually Comcast, and Comcast for us is one network. Okay, so
you're talking about the 36,000 ASs.
Yeah.
3/4 of those are connected to more than one.
At least, yeah.
And I think you said this, but what percentage of how many stubs are there in general?
85%. So of 36,000, about 30,000 of them are stubs. This is the number of ASs, and we have about 5,000 or 6,000 ISPs. Okay, so people who actually make money from service.
Okay. Is it actually true the stubs pay in proportion to how much traffic they send? It's not like a fixed monthly fee.
Well, it could be capped, but it's sort of commensurate. You know, you may have granularity, but it's commensurate. So we model it as, we can't model the granularity of all the payment agreements, but yeah, there is scaling that way. Yeah. Okay, so here's our guideline for deploying secure routing. Okay, so the first thing that we say is we want secure ISPs to at the very least break ties in favor of secure paths. So the example I showed you before, what we had was this guy, he's learning 2 paths, one of which is secure and one of which is insecure. Because these are equal length, he should choose the secure one. Right? So we could have said that the very, very first thing you should do is prefer secure routes. Right? That would also be nice for us. That would be better for security. That would be better for everything. But the problem is the ISPs probably won't buy it. If we tell them that now you have to change your routing policies, that secure routes is the most important thing, you know, bypass all your other considerations and take security first, they're not going to buy it. So we said, okay, just make sure that you break ties in favor of secure routes. So this was sort of the weakest condition we could think of to get this to work. The next thing is we have early adopters. So let's pick a couple of early adopters to deploy this protocol. And the final thing is that we have to deal with these stubs. So like I said, the stub is not Yevgeny at home, it's Bank of America or Boston University, okay? So these are like pretty decently sized network that speak BGP, but they're not really, they're customers, they're not providers. So how do we get these guys to become secure? So here's what our strategy suggests. As soon as this ISP here becomes secure, what it should do is its job is to now upgrade its customers. Okay, so if I'm a stub and I'm connected to this ISP, my stub should go and have a project in which it upgrades me. Okay? And how should it upgrade me, and why is this even a reasonable thing to claim? So the idea is that these stubs, because they only act as sources and sinks, the only routing announcements they make are for their own prefixes. Okay, if I'm a sink of traffic, the only announcement I have to make are for the prefixes that originate at me. So for the guy that we saw before, it was, let's say 10.10.10.0/24, right? The only announcement I'm going to make is pertaining to this particular prefix. Okay, so it's basically one prefix out of 36,000. Okay, so that's the only announcement that's going to come out of me. Everything else I receive, the only thing I send is stuff pertaining to me. Okay, so because we're only sending announcements that have 1 hop long, and because they're only for basically one prefix out of 36,000, you can have these guys only sign and not verify, and the overhead of that is much lower. It's a software upgrade rather than a hardware upgrade. Okay, so now I don't need to keep the public keys of the entire internet. I just need my own secret key, and I only need to sign. Okay, so the idea is that because this upgrade is so much cheaper, we want the ISPs to do it to their customers, And actually, the fact that it has no hardware upgrade doesn't come from me, it comes from the router manufacturers. So I feel really good saying this now because one of the router guys got up and said this at the last meeting that I was at. So it's cheap, and the security impact is only minor because you're not verifying, but because the announcements terminate at you, by not verifying, you're only hurting yourself. Okay, so the impact of not verifying is quite small. So, yeah, Yevgeny.
How dynamic are those Bank of America and Boston University?
In what sense?
Well, do they just have, like, when they join, they just tell once, essentially, this IP addresses and they never change?
But there is a timestamp on these messages that I haven't shown to prevent replay attacks. So you do have to what they call re-beacon. You have to re-announce just because otherwise the timestamp will go forever. So it's not very dynamic. It's very slightly dynamic. Like you could think of days or half day or something like this.
But I mean, why should those guys be secure at all? Because somehow, if ISP knows that this Bank of America is just pretty much connected to me and it never changes, it will just kind of dynamic. I mean, just
so one solution is to have the ISP to do the signaling for him.
Right.
So he could take the public key of him, own the public key of Bank of America, and do the signaling for him. And that's actually another solution we propose. But that means Bank of America loses its ability to do the announcement itself. But that's also fine.
But that's my question. Why would it even do the announcements? Because if it never changes, it just...
Well, maybe if it has two providers, and maybe it wants to announce it this way but not that way, this allows him to do it. It allows him to decide that I want this prefix to go out on this edge and then not on this edge, for example. Okay, so it gives it control. Is there another question? Yeah.
It would seem like more importantly, it would allow him to prevent, the Chinese ISP from hijacking his traffic.
Right, so he doesn't have to put his trust in anyone except for himself. I mean, ideally, if this ISP is not the Chinese ISP, then he might trust him to do the announcement for him.
Right, but if he only signs things for his two local ISPs, then anybody that's got a secure route to is not going to get tricked into routing through the Chinese ISP because that's not going to be able to get a signed thing.
Right. Okay, so I want to quickly finish. So this is basically what we say. So if you want to know what our main contribution, it's right on this slide. Okay, so this is how we propose deploying the protocol. Make sure it impacts routing decisions. Make sure that this process happens, and this is extremely important because of the structure of the network, right? We want the edges to have some reason of becoming secure, and the way we do that is by having their providers become secure. Okay, so we need to model if this works. So how are we going to model if it works? Well, let's take our network. Let's define the state of the set of the node that's secure. So this graph, those three yellow ones are secure. That's the state. Okay, and now we want to sort of model how deployment will go. Initially, the early adopters become secure. In every state, what's going to happen is that we're going to compute the utility for each ISP, given its current state. So for example, 8359, we'd compute its utility in the current state. And then we'd say, what happens if he became secure? How would his utility change? If his utility changes enough, so if it changes by, let's say, 5%, when he becomes secure, just looking at the current state of the world, then he'll also become secure. Okay, so this is a myopic process. You look at the world right now, you say, how much do I gain by becoming secure? If it's enough, I become secure. Okay, that's basically the whole model right there. So now, this is really hard to work with from an analytic perspective. We can show that things converge, blah, 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 but actually the real work is to simulate that this works. Okay, so let me, so I'm missing something very important, sorry. How do we actually measure the utility of these nodes? Okay, so the utility of the node is how much traffic routes through it. So this is how we measure utility. We look at the ISP, we look at its destination. So for every destination, we see a destination that can be reached along a customer edge, which means that the destination is somewhere down here. I'm getting paid for delivering to this destination. I count how much traffic I deliver to that destination, and that's the utility for that particular destination. Okay, so, and then I sum over all destinations. That's my utility. And now, in order to compute utility, all I need to do to compute utility is look at the state and decide how these networks make their routing decisions. Okay, so to decide how they make their routing decisions, right? So the point is I need to compute utility. I know the state, and that state fully determines how routing will go, given that I know how these networks make their routing decisions. So we have a model for how they make routing decisions, which is basically you're going to prefer to route through your customer, right? Someone who pays you is preferred to route to, over someone who doesn't pay you, over a provider, over someone you pay. So that's the first step in the decision process. So it's sort of what is the cost of this route? The second step is how long is this route? The third step is this route secure? And then finally, there's a tie break if you need to do a tie break. Okay? And that will allow us to determine all the routing. Okay.
Because, I mean, for myself, for example, or do I do it empirically, or how do I do it?
So we did it empirically. We assumed that they had a global view. In reality, it's not as easy to compute, but we just did it to do the simulations because we didn't know how else to estimate. Yeah, we assume that they have a global view. Yeah. Okay, so.
But they could measure, right? They could measure how much traffic they are getting, a fraction of traffic which is secure.
Yeah. So estimating how much more you get by becoming secure is something you might be able to test. It's not super easy to test, but we put it in the model because we didn't know how else to measure a gain. So we just said, let's look myopically and see how much you gain.
It's hard because once you do the test, you need to kind of employ PKI. Once you employ PKI, well, I mean, you kind of already invested the cost.
So a test is like traffic flow kind of thing. If I just become secure and I know these 4 are secure, I just say, well, fraction of traffic going to that.
But one piece of change may have cascading impact.
Yeah, it has a cascading impact. So it is in fact the cascading impact that makes things interesting. So it's really, it is quite hard to measure. Yeah, it is quite hard to measure. But we just, again, there's probably ways to estimate it. We could have noised it up a little bit to account for estimation errors, but we didn't. That is actually one thing that we talked about doing, but we didn't actually have time to do it.
I mean, you can do it by experiments, but even global thing, it's not obvious to me how to compute it. I mean,
no, it's not. It's not. No, it's not. Okay, so actually just to state, since I'm at Microsoft, the way the simulation is, by the way, an order n cubed simulation. I don't know if you can see that from here. The reason is you need to compute the all pairs shortest paths for each one of these ISPs. So all pairs shortest paths is n squared, and then there's n ISPs, so it's an n cubed algorithm. That's n is this, 36,000. Okay, so it's big. So this is why I had a lot of help from Microsoft SVC, from Frank McSherry and Mihai Budiu, who let me use DryadLink. And so each one of these simulations took half a day to do. Okay, so they were pretty fun. That was our big job last semester. Okay, so let me show you some of the simulation results. So here's a simulation that we ran. We picked 10 early adopters. So that, by the way, these are their network numbers, not their size. Okay, so ignore these numbers if you don't get scared by these numbers. This is the wrong slide. I should have taken this off. But anyway, these are the 10 early adopters that we picked. So the early adopters included content providers like Google, Microsoft, Facebook, Akamai, and Limelight. So these are the biggest content providers on the internet. Then the 10 biggest providers, sort of networks that act like backbones, we turned those guys on, and then big content providers, and we saw what we got. And the exciting thing is that if we assume that the thresholds of all these nodes, so they need to see 5% increases in traffic before they turn on, then we get 85% of these networks becoming secure. Okay, and by the way, it's not just 85% where these are all stubs. It's 85% where 65% are ISPs. So 65% of the nodes in the core became secure, and a total of 85% of nodes became secure. So we really did see significant adoption in the simulation. And let me show you why. Sprint was one of our early adopters, and this was the flow of traffic. Right? So what happens in the first round is that this guy says, if I become secure, then my stub becomes secure and the traffic shifts. Right? And then the next thing that happens is this guy will say, wait a minute, I'm losing money. Let me become secure, and then he becomes secure, and the traffic shifts back. So his utility goes up. And what you start to see is longer and longer paths. So this guy is going to say, if I become secure, if my stub becomes secure, the traffic shifts, and I get more money, right? Because I'm delivering traffic to a customer. And then we get even longer paths where this guy says, okay, now I have this long, nice path here. I can become secure, and my stub will become secure, and I can grab the traffic this way. So we really just see this jumping in traffic. And the interesting thing is that we only need to assume that they break ties on secure routes. We don't have to assume that they prefer secure as the top thing. Yep.
What if you give them a little bit of ability to see in the future? Won't they see in the long run it's not going to gain me anything?
Yeah. Okay, let me answer Vinod's question. I have a slide for you. Okay. I have. Yeah.
What are the guys who resist this process? I mean, are they the guys who have just one stub who's only connected to that?
Yeah, exactly. When we looked at the guys who never secure themselves, they tend to be providers with a lot of stubs that are single-homed, and they don't have any competition, so they just don't become secure in our simulation. Yeah. That's true. And then there's also the frog boiling guys. So I'll show you frog boiling guys. So here are some guys, and let's look at how their utility changes. Okay, so this one became secure in round 4, 5, and never. So this is the round 4 guy. What's happening is that people are becoming secure, and he's losing traffic. right? But he never gains enough by becoming secure. At this point, he sort of sees that by becoming secure, his utility will increase more than 5%, so he secures himself. And then we can see that his utility goes up for a while, right? Same with this guy. This was the guy who became secure in the 5th round. He turns on and his utility goes up, but then it drops. So what we're seeing is that sort of like at this point, what the simulation was showing was around here, basically everyone who was going to be secure was already secure. And so what's happening is this traffic shifted back to normal. Okay? This guy was like frog boiling in the sense that he only loses about 4% of traffic. He never gets to 5%, so he never turned on. The threshold was too high for him. But what we do see is the ones that are secure, their utility is sort of higher at the end of the game than it was at the beginning, and the ones that don't become secure, their utility is lower. So the reason we see this kind of behavior was that this is actually a zero-sum game. Like, we didn't assume that more traffic appears in the course of the simulation. It's just this customer traffic that's moving around. So it should actually go back to this state. But what we do see is we see these periods where they're sort of getting a lot of utility out of the protocol, and then it goes back down to normal. Yep.
To have a paradoxical effect, because you're saying updates are myopic, so I'm kind of saying, okay, there are a lot of insecure guys, I'll become secure, my utility goes up, but because I became secure, a bunch of other guys became secure and they stole all my traffic.
They stole my traffic, so it's much worse for me.
So it's conceivable, it seems like it could happen, I don't know if it's...
I have an example I'll show you. I think I want to end, so I won't talk about that too much, but yeah, like all kinds of strange things can happen. When we looked at this on average, we saw that generally when you become secure, your utility will go up and stay up for a while. Now, in fact, there were simulations where it got stuck very quickly, like it got stuck with like 20% becoming secure. When it gets stuck, if you're one of the secure ones, your utility is up and it stays up because the traffic doesn't shift back. Right, so sort of two outcomes. One is the process gets stuck and you get more traffic. Or two, the process doesn't get stuck, you lose most of what you gained, but now you have a secure internet. So it's sort of better for you to become secure. Okay, so that was, huh?
Traffic at the end?
Well, this guy didn't. He lost relative to here, but he didn't lose relative to the initial state. Right? He's still better off than he was at the beginning. Yeah. Okay. So we did a lot of work trying to understand who the early adopters should be. I guess I'm going to skip this, but we have many simulations looking at the effect of different thresholds and who should be secure. What we ended up finding that is it's important to have the tier ones. The tier ones are the providers at the core, the backbone networks, becoming secure. The reason for that is because the backbone networks have a lot of stubs attached to them. And so turning on a backbone network sort of gets you a lot of stubs, and it's just going to it's amplified the effect because they have such high degree and so many stubs attached to them. The content providers have very high degree, but most of the degree is through peering. So what Microsoft does, by the way, is it says, hi, I'm Microsoft, I'm in this data center, I'm in this internet access point, please come be my peer, it's free. And everybody does. So they have very high degree, but they don't charge any money, so they don't have any stubs. So in our model, they didn't really upgrade any of their neighbors when they became secure. Okay, so yeah.
I mean, did you also simulate where some small fraction use a security-based incentive to switch? That may avoid some of these things. So for example, Microsoft would have the security-based incentives.
I see. Yeah, that would have been folded into our early adopters. So our early adopters are the only one with security-based incentives, and everybody else is just playing on traffic volume. Yeah. So hopefully these content providers, you can make the argument that they have security-based incentives to do this. But we didn't mix that. No, we didn't mix that in. Yep.
Yeah, I didn't quite get the incentive of why an ISP will turn the stubs on.
Yes.
Especially when the stubs are provided maybe by multiple ISPs. So why I should use my money to turn it on?
Yeah, exactly. So actually, one of the goals of this stuff was to talk about government incentives. So we actually do talk to the government about this. And this is where we think that the government incentive should go. So it's not completely clear what his incentive is to do this, right? So we want to create artificial incentives for this to happen. Okay, so this is really the place where we think, like, if you want to inject money into this process, inject it into having him turn on his stubs, and inject it into the early adopters, because that's where there's like a lack of incentives. There is also sort of like, if you become secure and your stub becomes secure, then you can steer the traffic over to the stub, right? Like if you see, you see what happened here was the traffic used to be here, he becomes secure, turns on his stub, and now he can steer it over because this destination, he won't be able to steer it over if this was insecure. You see, because this would not be a secure path. The traffic wouldn't shift this way because this is not a secure path to this destination. Okay?
In your model, since like the model
stub as a sort of a passive entity instead of
exactly.
a very...
He's not a player. So in the game, the only people, the stubs are non-players. We still have to compute the routes to them and the routes that they choose, but they're non-players. The players are everyone else, the non-stubs. So the 15% of nodes are the players.
But in reality, are they actually players themselves? Because they choose, as you said, they choose to announce the ownership of prefix to maybe different providers.
Yeah. So one way to model the fact that they're players is they could start creating links. In some sense, they act as players in the following way. They choose routes. So somehow, you can't see it in this picture, but imagine a stub choosing a route through him as opposed to through him. He's going to increase his utility because he's got more traffic. So in some sense, our model does incorporate the stubs as players because they make routing decisions based on security. Right? We found that we didn't even need that in our model. Like we basically get the same results whether or not they make decisions based on security, but one way to model them as players is to have them make decisions based on security. Another thing that we didn't do was that you might imagine people forming and breaking links because one guy's secure, all of a sudden everybody's forming links to him. We didn't do forming links because it seemed like a very difficult thing to model because you might need to incorporate geographic information and we didn't have good data on that, so we just didn't do it. But that's another way you might think about like the graph reforming as a result of this, which we didn't do. Okay, yeah. So I want to finish in an hour, so I'm going to try to stop. Okay, so Yevgeny asked me if anyone ever wants to turn off. Yes, the answer is yes. You can have weird things. Can I take 2 minutes and show this? Okay, so let me show you, if you use a different utility model, why someone might want to turn off. Okay, so one thing, if you start working on BGP, anything crazy that you want to happen can basically happen. So let me show you something crazy that can happen. So these guys are secure. Okay, this is, by the way, out of a simulation. So that I set up very, very carefully to make this bad example. Okay, so these guys are all secure. This one's not secure. Okay, so let's look at routing in this network. Our destination is here. Right? This guy, Akamai, who's, by the way, a big content provider, is going to learn two paths, an insecure one, because this node's insecure, so this path becomes insecure, right? And a secure one, okay? They're equally long. They're both through providers, so they're equally good paths, so he's going to choose the secure route, and he's going to route like this, okay? Because this is secure. Okay, now let's look at the utility of him. He's paying to receive traffic this way. Okay, that's not so great. Okay, now let's imagine what happens. So he's paying to receive traffic from his provider. Let's see what happens when Akamai becomes, when 4755 becomes insecure. Now all of these paths are insecure, right? Because this one in the middle is insecure, so that what used to be secure here is now no longer. So he's learned two insecure paths, and what happened in this simulation was the tie break went this way. Okay, so now if we look at the utility of this node, he's getting money from a customer, and that's better for him. So his utility goes up. Okay, so what I'm showing you is an example where you might want to undeploy because it might get you more revenue. And in fact, this was so much fun that we thought we can show oscillation examples, and it was even more fun, we can show piece-based completeness. Okay, so we can show that it's piece-based complete to determine if oscillations will ever occur in this graph. Okay, so you know what you can do with these things is you can make the game of chicken out of these things. And if you're interested, I can show you how to make chicken out of this thing. And then if you have a chicken gadget, you can actually hold states. Then you can build a Turing machine, and you can start to show it oscillate. So we actually did do that. And so we were able to show that it's hard. If you have a utility function that allows nodes' utility to depend on where the traffic comes from. By the way, the other stuff that I showed you, we did not make the utility depend on where nodes' traffic came from. We just made it depend on where it was going. In this model, I'm caring about the fact that it's coming in from a customer here versus a provider there. Okay, so we didn't, in most of our simulations, we took this out because we didn't want to deal with oscillations. But if you want to start thinking about where the traffic came in, then you can start to have oscillations and all kinds of bad things. Although realistically, I don't expect oscillations to happen because the structures were so crazy that we don't really expect to see them. But in terms of actual undeploy, yeah, I expect to see cases where you don't want to get the traffic this way. So you may want to become insecure. Okay, so just to conclude, what drives BGP security deployment? So we've looked at multiple approaches, one of which is security, which was sort of our very clean graph theoretic formulation. And then the other one, which is attracted traffic, which was much more messy because we had to incorporate business relationships and count traffic volumes through networks. So it's much harder to work analytically with these things. If you ask me how we actually create a market for this deployment, the idea that stubs need to be turned on by their providers is extremely important. Our simulations would just get stuck without this. We think it's very important that route selection is influenced by BGP security. So if the more secure you are, the more traffic you get. And the government incentives should go in two places, having the ISPs turn on their customers and having the early adopters turn on. There's many, many open problems in this. We don't have good algorithms to find early adopters. So in our second paper, we just did heuristics, large degree nodes, high volume traffic nodes, things like this. In the first approach, we have some very restricted algorithms so far. The next question that we're currently working on is trying to understand what happens in settings where there's secure nodes and insecure nodes. What are the security guarantees there? So it sounds like something people should have looked at, and there has been a little bit of work on that, but there's no even sort of metric of like, you have 100 secure nodes on, what kind of security does the internet get? We don't really know how to measure that, so we're sort of working on that right now. And that's it, and this is 3 different papers, one of which we're still working on. Okay, thanks.
So what is the, I mean, I don't know, you didn't mention it, so what is the effect on functionality? Because presumably security is kind of cool, but if you're saying in some of your simulations, you know, it could be that some guys will get security, all the traffic will go through them, and the other guys will not care because it's kind of too late. And now, of course, you killed everything. It's like so congested that nobody wants to use the internet. So
yeah.
What is the effect of, like, I guess, social utility function?
Yeah, so we haven't included capacities of links in the models, and that's really problematic. So when I spoke to, last week I spoke to the Network Operators Conference on this, and I thought they were going to crucify me because we didn't incorporate capacities, and they actually didn't crucify me, so I was very happy. But we don't know how to do that yet. So some of the things that bothers them is that because their links are very carefully engineered, even the claim that we're making that they should break ties on secure paths is sort of scary to them because they're afraid that they'll burn out the links by doing that.
So you're saying nobody has done the studies how security will affect functionality?
We don't know. We don't know. So that's another important open thing that we don't even, at the moment, don't have the data to even analyze. So that would be an important thing to try to understand. Some of the guys I spoke to said they would be willing to do it if like all their neighbors did it at the same time. They could sort of minimize the impact, or they could pre-test with one destination and see what it does. But I haven't really, we don't really understand that. In fact, the idea that this should even impact traffic engineering is not really, wasn't really thought about until we did this paper.
When you were looking sort of at the payments models that you're optimizing, do people tend to pay by the packet or pay by the width of the pipe?
It depends. Sometimes it's by the width of the pipe. Sometimes it's by the packet. I think in Europe it tends to be more by the packet. Not exactly by the packet, but sort of much smoother. And then a lot of other places it's sort of by the pipe. So sometimes it's like if you exceed the pipe by something, then you get paid. But a lot of the time, I think it's like 95th percentile utilization, and that's what you pay on.
And does it ever vary according to where the packets are going?
I don't think so. I haven't heard.
Because it would seem like when you're talking to an ISP, sometimes you're sending it back to somebody else that you can charge.
Yeah, I don't think.
And sometimes it's just somebody that's going to charge him.
No, I don't think
that is a net neutrality argument. Isn't that the net neutrality?
They should charge you more for packets that are going further. That's true. Yeah, that would violate net neutrality.
So net neutrality says that they're not allowed to charge differently?
Well, it's not yet in place. Right?
Yeah.
It would say that.
Let me show you an example of something that they might do.
Have that, allow that or not allow that.
Okay.
Here's an example of something they might do. A routing policy that sometimes people use that we don't really see often is that they'll have a customer here that pays it for service, and they'll only announce to the customer links through other customers and through peers. But they won't announce to this particular customer any paths through its provider because it doesn't want to have to pay for this customer. So you have these sort of semi-customers where they don't get a full set of routes from this guy, just the peering and customer routes. So that's one way to enforce what you're saying. But we didn't model that in this paper. This is kind of more rare, but you do see it. Yeah.
Do you have a plan in the future to model more complex incentives? Because right now the model is a little bit simplified, as the market economy is the only incentive.
Yeah.
There's other political issues.
Yeah, no, we haven't figured out how to do that. That would be good to do, but we don't have plans, nor do we know how to do that at the moment.
Thanks, Shirley.